Yeah, my name is A Carrasco. I'm the CEO of M.Sc, which is a company located by the east coast of Spain, very near to Alicante. What I'm going to present you today is a CubeSat platform that we've developed to make modelization and tests within LEO orbit in principle. And this is going to be the outline of the presentation. First of all, I will present the purpose and objectives of the NaoSat platform. After, I will describe the platform itself, the service module, and the module for the payloads available for experimentation. I will present two missions that we have so far, and then the final purpose of the experiments intended for the platform. The object of the platform is both from the scientific point of view, is to test and to prove the models that we develop on Earth within LEO orbit or within orbit. And from the market perspective is to test components and subsystems in LEO orbit in order to increase the TRL of any component or any subsystem. The reason of that is the introduction of very new components due to the recent developments that are pushing the requirements of the components used within the space industry. Of course, any change in technology needs new qualification processes and the ultimate environment to prove the new technology for components and subsystems is the real test within the environment to increase the TRL of the system. So that's why we developed this platform to make these in-orbit tests. The platform is based on what is called the CubeSat standard. It's a 3-unit CubeSat. For one unit, we understand a CubeSat of 10 centimeters times 10 centimeters times 10 centimeters. So it's a very small cube. For that, we use a cubes built with 3 of those units. It only can have inside 3.5 kilograms, and so for the service within that space, we have the space for the service module and for the payload module. The service module uses 1 U, so it leaves two U's, mostly 20 centimeters times 10 centimeters times 10 centimeters for the payloads. The average power of the satellite is surrounded by the solar arrays. There is very small power available because the surface is very small. So from the 6 watts produced by the solar arrays, for the solar arrays, only 3 watts can be used by the payloads, although that's the average or mean power, although we may provide peaks, power peaks for payloads that need it. We provide pointing, accurate, the attitude control with some accuracy, and we have as well telemetry, telecommand, and everything that you may expect from a platform to service the payloads. That's the main characteristics of the platform, and this is the small one is the one we have developed and we have ready as well today. And this big one is evolution on the small platform that we use 6 modules stacked together to make a bigger platform. But this one is something we are developing at the moment. It will be bigger. We'll be able to provide more power to payloads and more space available as well. And it's more suited for optical payloads because although they don't have that much mass, they need some bigger apertures to be tested. This is schematics of the payload from the electronics point of view. It's the service module is on top, and the payloads go here at the bottom. We provide a fully protected platform with redundant switches that are able to stop the working of whatever is being used, even if, in the service module or in the payloads. And in case that a latch up or a single event is produced, the platform is able to automatically stop the payload or the thing that is malfunctioning and reset itself and continue working without problems. From the payload point of view, this is the space available, to nearly 20 centimeters, and this is the area available for the payloads. This is the platform, the service module, and the payload goes here. We provide a standard interface that may be stacked here, and that we may develop for groups that want to experiment and to include an experiment within the platform. Or we may provide an interface control module, a complete interface control module for a team of researchers to develop its own payload, or we may develop the payload for whatever needs of the team. This is a view, just an schematics view of the interface control document with all the things that we provide. And in summary, we have a standard communication bus available that is able to communicate with the payloads that are integrated to get all the information to characterize any payload that flies in the platform, with the final goal of the in-orbit characterization of components and subsystems within Earth orbit. So far, we have 2 missions ongoing. One of them is a platform to test some technologies from the Universidad Politécnica of Valencia. This will test 4 new technologies developed by researchers at this university, and 4 research teams have united efforts to provide 4 payloads into the payload area of the platform. This platform has been included into a launch program by the European Space Agency, and it's awaiting for launch in one future European Space Agency mission. This is one example of one of the payloads, the EQM of one of the payloads, which is a communication module in C-band, 5.8 gigahertz. The EQM to work to transmit with this carrier and to send data 400 kilobits per second with codification of turbo codes and convolutional codes. And this is the flight model of this EQM. This is the transmitter here, and this is one amplification module as an example of a standard PCB that may fly on the payload. Another mission that we are waiting for, that we are preparing, we are participating in a Phase A mission by the European with the European Space Agency to send a CubeSat to one asteroid that will have to one asteroid, and the mission will send an impactor to the asteroid and will try to divert the orbit of the asteroid a little bit to study what happens if we are able to alter the orbit of the asteroid. I tell this to you because this is an example of a complete modification of the structure maintaining the structure of the platform and the same philosophy for designing the electronics. It's a complete modification of the internal setting of the components to fit for this mission that we are under our study phase at the moment. And as final goal is just to provide, as I told you before, to extract the parameters from components and subsystems to alter the reliability calculations and adapt them for real standard real conditions that are not included in the actual mill Hamburg 217 Hamburg to calculate reliability calculation. And this is one tool that we have at this moment to provide this calculation and that we plan to adapt for the environment, for the LEO environment, once we have data from the missions that we are preparing with this platform. And this is my presentation. Thank you very much for your attention.